titrations now. So essentially what a titration is an acid plus a base, which will yield to them neutralizing each other. Neutralization. Which essentially what neutralization means is that they kind of, I don't want to say they cancel each other out, but they just kind of try to reach an equivalence point where there's as much acid and as much base in there. Well, moles of acid and base. So a titration is made up of two components, which is the titrant, which is equal to the substance being added. Oh my god, I cannot spell, I'm so sorry. Substance being added, and the analyte, which is the substance being titrated. As in, when you're performing a titration, it's the thing that you're titrated. It's the thing that's already inside of the flask, not what's in the burette. Alright, so then with titrations, depending at what point in a titration, your pH is going to represent that. So if you're in the beginning of titration and you're doing an acid and you're adding a base to it, then you're going to have a pretty high pH. And if you're towards the end of it, like you overshot it and you added way too much base, you're going to have a pretty high, well, you're going to have a low pH for the acid and a high pH for the base, right? But then there's such a thing as equivalence, which is what you're trying to shoot for in titrations. With an E or an A? Equivalence. I'm assuming it's with an E. Okay, but it's your equivalence point, which is where moles of your titrant equals your moles of analyte. And this is what we're shooting for whenever you do a titration. It's just that them being equal to each other, so that whatever's in solution can't really, I won't say can't really hurt you, but it won't have as much of an effect as it used to. Right, so with titrations, there's 3 separate kinds that you kind of have to recognize, at least for this course in Chem 1306, for like your class. And one of them is your strong acid being added to a strong base. Plus strong base. Yeah. So you're going to have your graph, which right here you're going to have your pH, and I'm going to label this as 7 because that's kind of our neutral point. And then your x-axis is going to be the milliliters of acid that we're adding. So this is kind of our titrant goes on the x-axis. And then on your y-axis, we're starting off with the strong base because we're adding the acid. So we're just going to put, because this is just a rough graph, it's not an actual plot point, so just somewhere above 7, and then it's going to go down kind of quick and then level off again. And then because it's a strong base, strong acid, our pH at equivalence is going to be about 7. So then now let's say that we're doing a weak acid, or no, a weak base being titrated with a strong acid. So this one essentially you're going to have the same axes as in pH in the y. I'm going to say this is 7. And then our titrant is still an acid, so it's still going to be our mils of acid being added. And like I said, this is a general graph. So above 7 anywhere. It's just that in this case, since it's a weak base, it's going to take a little longer to kind of flatten out and go off. And in this case, our pH at equivalence, is going to be less than 7. And that's just because we're adding a strong acid, so there's going to be more H's than you would with a base, just because this will fully dissociate. So you'll end up with more H's, and that's how you get your less than 7. And then our final scenario is a weak acid being titrated with a strong base. So in this case, that's when our axis in the, well, our x-axis gets different because our y-axis is always going to be pH. But now our titrant is a base, so then we have milliliters of base being added. And then since it's a weak acid, we're going to start off somewhere less than 7. And like the weak base, it takes a while to kind of curve off. And then at equivalence, our pH at equivalence is going to be greater than 7. And that's, like I said, we're adding a strong base. If you're basic, you have a high pH, right? So these are just rough sketches of what the graphs look like. So it's up to you guys to kind of be able to figure out if you have a strong, a weak base with a strong acid, or a weak acid with a strong base by looking at your graphs and being able to tell, like, oh yeah, the pH would be less than 7 because this is a weak base and that's a strong acid, and kind of like that. All right, so I'm going to erase this now, because what we're going to do now is actually go over an example of how to work out the pH of a titration and not of a strong, just because with a strong, all you have to do is whatever you have left over, you plug that into your pH or pOH equation, which is just the negative log of your OH or H concentration. But we're going to do a weak with a strong, because that's mostly what you guys are going to encounter with your exams with the professors that you have now. So let's say that we have so we're going to figure out the pH of a titration of a 40 ml solution of 0.5 molar NH3 by a 50 ml solution of 0.2 molar HCl, given that the Kb of ammonia is 1.8 times 10 to the negative 5. So our first step, because something to keep in mind is that in titrations, you're always going to be working in moles, because there's always going to be a volume change. So your concentration changes depending on your volume, right? Because concentration is moles over liters. So since we're going to be adding 50 mils to 40 mils, we're going to have a volume change. So our concentration is going to change. So we have to find our initial moles. So let's find the moles of ammonia first. So if we have a 0.5 molar solution, it's equal to X moles over liters. So we just convert milliliters to liters, which is a division by 1,000. So we end up with 0.04 liters, and we end up with 0.02 moles, and that's for NH3. So then now moving on to HCl, we have 0.2 molar is equal to X moles over, again, convert the 50 mils to liters by dividing by 1,000. So we end up with 0.05 liters So X is equal to 0.01 moles. So now we write out our expression. So NH3 plus HCl yields to NH4 plus Cl minus. So we're going to do ice tables again. So initially we have 0.02 moles of ammonia, 0.01 moles of hydrochloric acid, and 0 moles of both ammonium and chloride. So our change with titrations is always going to be our limiting reagent, which in this case it's the 0.01 because that's the smaller number of the two. So our change is going to be minus 0.01 minus 0.01 plus 0.01 for our products because that's what's being created, and our final slash equilibrium, but I'm going to say final, is 0.01 moles 0 and 0.01 for both our products. Right, so then if we were labeling these with our Bronsted acid, Bronsted base, conjugate base pairs, this is our base, this is our acid, so this is our conjugate acid, and this is our conjugate base. This one connects to this one, and those two go together, right? Okay, cool. So just keeping that in mind. So now what we're going to do is that whenever we solve for pH, we always use concentrations. So we're going to have to convert to concentration using our total volume. So doing the NH3 one first, we have 0.01 moles. And now, since we added our 50 mils to it, our 50 mils to the 40 mils, we have a total of 90 milliliters, which is just our 0.04 liters plus 0.05 liters, which would equal to 0.01 moles over 0.09 liters, which is about 0.11 molar, and it's the same formula for NH4 and the Cl minus, and since we end up with the same concentration, 0.01, 0.04 plus 0.05, we end up with 0.11 molar as well. So now, knowing that we have a Kb, a conjugate acid concentration, a base concentration, we can use our Henderson-Hasselbalch equation for pOH because we have the Kb, which is a base, and we have the base. So all of those lead to a pOH. So we're going to do the Kb, which is a negative log of 1.8 times 10 to the negative 5. My underline looks like I crossed that out, but that's just it being underlined, I promise. Plus the log of our conjugate acid, which is 0.11, over our base, which is 0.11. So then our pOH is equal to 4.74. So our pH is equal to 14 minus our pOH, which is 4.74. And we end up with a 9.26 pH, which makes sense because in the end we still have more of our conjugate base than we did of our acid that we were adding in, and we're not at equivalence yet, so we shouldn't have a pH lower than 7 yet. So pH is 9.26. So like I said, to keep in mind with titrations is that you're working in moles for the whole ice table, and once you reach the end, you convert back to concentration by dividing by total volume. So it's by adding the 40 and 50 mils that we got the 0.09 liters. Just because, like I said, titrations, you're adding something to something, so you're going to have a volume change. Okay, so then I'm going to erase this problem because the next thing that we're going to do is we're going to solve for the pH of a titration at equivalence point, and those are just a little bit tougher just because they take an extra step. Like you can't use the Henderson-Hasselbalch equation on them. And you'll see why in a bit after I erase this. Oh my god, I need to find a way to just erase the whole screen, but it's kind of therapeutic to just erase everything. Okay, so titrations at equivalence point. So the way that these problems are usually worded, they never tell you that it's moles of this plus moles, like moles of that and stuff. Like you have to figure it out. So it tells you to calculate the pH at equivalence. At the equivalence when you have 15 mils of a 0.3 molar acetic acid, and it's being titrated with 0.02 molar of sodium hydroxide, and then Ka for acetic acid is 1.8 times 10 to the negative 5, which I know this number gets used a lot in these examples in your workbook and stuff, but it'd be like that. So then again, our first step is that we're going to solve for the moles of acetic acid, which is Ch2. So we have 0.3 molar is equal to X moles over 0.015 liters. So we end up with X is equal to 0.0045 moles. So now we're going to solve for the volume of HCl because we're given the 0.2 molar, and since it's at equivalence point, that means that your moles of titrant is equal, well, moles of titrant is equal to your moles of your analyte. So if we have 0.0045 moles of acetic acid, that means that we're going to have 0.0045 moles, not hydrochloric acid, my bad, of sodium hydroxide. Yeah, you have to have a base and an acid. That's my bad, guys. But yeah. So then we have our X liters, and now we're just going to solve for X, and we end up with 0.0022, wait, 0.0225 liters. All right. So then we're going to set up our titration, which is going to be acetic acid plus sodium hydroxide yields acetate ion, well, sodium acetate plus water, which usually that's what you get with titrations most of the time, is a salt and water. And I say most of the time because in the problem that we did before, we just got kind of like their ions, but that's fine. So initially we have 0.0045 molar for both, well, moles, and none of these to begin with. And the change, our limiting reagent, it's the same thing. So we're going to have 0.0045 because it's the same number. So there is no limiting reagent is what I'm trying to say, because there's no change. So then finally you have 0, 0, and 0.0045. And this is what I mean by we can't use a Henderson-Hasselbalch here, because Henderson-Hasselbalch, you do your your concentration of your, what is it, conjugate acid or conjugate base over your acid, and you can't divide by 0, like you just can't, your computer will explode. Yep. So we have to do something different here, but first we are going to convert it back to concentration. So there's only one thing we can convert to concentration, and that's our sodium acetate. So we're going to do 0.0045 divided by total volume, which is 0.015 plus 0.0225. So then .015 plus 0.0225 gives us 45 over 0.0375. So then we end up with 0.12 moles. Oh my god. Alright, so then essentially what we have to do here is find the pH of our salt. And like I said before, salts dissociate completely, so that you have, so we're going to go from here to here. So you're going to have NaCH3, COO, breaks apart fully into Na plus CH3, COO minus. So you're going to start with 0.12, 0, 0. And then finally you're going to have 0 and then 0.12 and 0.12. Just because, as I said, with salts, it's dissociation completely. So what you start off with is what you end up with. So then now we're going to take this part right here. And we're going to set up an equation of a weak acid, weak base thing, just how we always have. So we're going to end up with our acetic acid plus OH minus. And then we're just going to solve how we always did for our OH minus concentration. So this is 0.12, condensed state doesn't matter, 0 and 0. Our change is minus x plus x plus x. At equilibrium, we have 0.12 minus x, x, and x. So now because we're dealing with OHs, we have to change our Ka into Kb. And to do that, if you guys recall, Kb is equal to Kw over Ka, which is equal to 1 times 10 to the negative 14 over whatever our Ka is, in this case 1.8 times 10 to the negative 5, which should give us 5.56 times 10 to the negative 10 for our Kb. So then now we just plug that into the equation. 5.56 times 10 to the negative 10 is equal to x squared over 0.12 minus x. And this number is small enough that we can discard this x. And so we just solve for x. And we should get 5.56 to the power negative 10 times 0.12 square root of that. So x is equal to 8.17 times 10 to the negative 6, depending on your rounding. So then we can plug that into our pOH formula because X is our concentration of OH. So pOH is equal to the negative log of 8.17 times 10 to the negative 6. So then you solve for that, and the pOH should be 5.09, around about there, but we're looking for pH, so pH is equal to 14 minus 5.09. So then you get pH is equal to 8.91. And again, that makes sense because if you guys recall with equivalence point pHs, if you're doing a weak base, which in this case we are because it's acetic acid, plus a strong base, NaOH, your pH should be greater than 7, and it's greater than 7, so that checks out. So, like I said, equivalence point problems are well, they're not a lot harder, but they just have more steps than not at equivalence, just because you can't do the Henderson-Hasselbalch. But that's pretty much it for titrations. So don't panic. Like I said, if you guys have questions, you know how to contact me.